This episode is brought to you by GPRS. Construction professionals know that utilities and concrete reinforcements can cause big problems when you're on the job. GPRS helps you avoid them. We use ground-penetrating radar to detect rebar, conduit, and post-tension cables before you cut, core, or drill. And our concrete scans are 99.8% accurate. We guarantee it, helping you reduce hits, downtime, expenses, and keep your people safe. To keep your job site safer, visit gprsinc.com. This episode is brought to you by Concrete Logic Academy. If you work in concrete, engineering, construction, or ready mix, you already know most of what matters isn't taught in school. That's exactly why we built the Concrete Logic Academy Unlimited Pro membership. You get unlimited access to 25 concrete courses, plus real-world breakdowns, research, and a community of professionals solving the same problems you are. Instead of paying for one course at a time, you get the entire library in one place, built for how you actually work. No travel, no hotel ballrooms, no sales pitches, just practical concrete knowledge you can use on your next project. Start your free trial at www.concretelogicpodcast.com/pro. If you're a ready mix producer and you've been trying to figure out how to actually train your team, this is for you. We built the Concrete Supplier Playbook Foundations inside the Concrete Logic Academy specifically for producers that want their people to better understand the concrete they're selling and supporting. It's simple, on-demand training your team can work through at their own pace and start using right away. For podcast listeners, we quietly opened up a limited Founding 300 group. If you want to see what it's about, go to concretelogicpodcast.com/founding300.
What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandit.
And welcome to another episode of the Concrete Logic Podcast. And today I have Dr. Jon Belkowitz back on the show for the, I don't know, we're getting close to 100 times. Something like that.
What? I better get a T-shirt.
No, not even close. How today, if you've never designed, I don't want to say designed, if you never came up with your own concrete mix design, we're going to show you how to do that today. So stick with us. But before we get started, I want to remind you how you can support the show. There are a couple ways. Go to concretelogicpodcast.com. And up at the top menu, there's a Ask Seth button. It's up at the top navigation menu. Ask Seth. You're laughing. You click
on an Ask Seth T-shirt. I want a T-shirt that says Ask Seth.
Yeah,
that's a great idea.
But anyways, you click on that, and that's a way for you to shoot me an email. And what I'm looking for are topic or guest suggestions. So if you want to hear Dr. Jon back on, or you want to hear him talk about something specific, reach out, or any other topic you want to hear or guest you want to hear from. That's what I'm looking for there. And if you rather leave me a voicemail, there's a at the bottom right-hand corner, there's a little microphone there. You can click on that, and it'll record you right over your computer or your phone if you're using the if you're on your phone, and you can leave me a voicemail. Same thing. Give me a topic. Give me a guest suggestion. because this is what the podcast is all about. It's about what you want to hear, what you want to learn about. And the second way is if you get some kind of value out of today's episode or any of the 150 plus episodes we put out there, you can donate to the show. And how you do that on the same homepage of concretelogicpodcast.com. There's a donate button, big blue button in the upper right-hand corner. Click on that. And there's no set amount. You just give what you feel was the value you got out of the show. So that's how that works. Another way,
No.
Dr.
Set
John.
amount. Don't be cheap. Advertise too. Get your PDHs here. Seth doesn't know it yet, but some of his PDHs are given away for free.
Hey,
it's
easy.
such a low cost.
We don't. I want to go back because someone actually sent in a donation. I want to thank them. Joseph Swan donated to the show. Thank you, Joseph.
Thank you, Joseph.
Appreciate the support. So he'll be listed as a producer of the show in the show notes. So check out the show notes. So he will always, forever, as long as the podcast exists, will be attached to this show. How cool is that? All right. Now we'll get to what you're talking about. You're a professional engineer, aren't you?
Me? I hope so. Yeah.
Yeah. And
I put the letters at the end. Right.
Yeah. You got to take classes to do whatever.
PDHs. Yep.
Yeah. Every year.
Oh, yeah. Yeah. And I
Yeah.
think it's a bunch of classes and they're not inexpensive and they take a lot of time.
Yeah.
The PDHs. So I normally go through PDH engineer, which is really cool. Read about the Hyatt Regency disaster, the Liberty ships, concrete stuff, steel stuff. There's a whole bunch. But what I like about your PDHs is they are directly concrete related. Although PDH engineer does have concrete stuff, it's out freaking dated. And I mean, shoot, if you took all of Bob Higgins' podcasts and you made quizzes out of those, I would pay big money, more money than you're currently have. And I'm not trying to, break the bank for anybody here, but what is it? You have 9 PDHs?
No, we have 25 courses right now. So
what do you sell them for, I meant?
Well,
The
you
bundles.
you can either do a couple things. You can either go on there and buy them individually, which is like the other websites have out there, like $30 each. So if you think about that, if you bought them individually, it'd be 30 times 25, be $750, which is a lot of money. Or you can get a monthly membership on the Academy for it's $39 a month. So you just pay by the month, go in there and do as much as you want and stay and you can get on there and there's other features in there. So just go to concretelogicacademy.com, check it out. And there's also links on the concretelogicpodcast.com. So check it out.
Well, what I like about these, I like about these is that I'm listening people that I want to learn from, that I know and I already have like trust and faith in what they're saying. And I'm just I already have learned from them. And now I'm just continuing my education and I get credit for it. $750, you have to spend it anyway, or whatever equivalent that is. I would rather do it this way, enjoy my time instead of having to force myself.
Yeah, and then it's a community. There's everyone that joins they're in there, so you can ask questions or just say hi. It's kind of a little social network for Concrete Logic folks. All right, but with that, let's get into today's episode. So again, I'm going to learn with everyone else today. We're going to make our own mix design. So I think you're going to kind of explain how we come up with a cubic yard of concrete first, right?
Mm-hmm.
What's the pieces and parts of that? Why it's a certain amount?
You got it, man.
All right. Well, get us started.
So concrete mix design, I call it, especially when you use the ACI 211 method, I call it a choose your own adventure. Right. And I'm trying to be cute and funny, which of course I am, but I'm also trying to make what could be death through mathematics into fun with mathematics. Right. Now, when it comes to concrete, it's a very easy approach. Concrete, as Seth already stated, is sold here in the United States in 1 cubic yard. And if you don't know what a cubic yard is, imagine a block. Sorry about that. Imagine a block that's 3 foot by 3 foot by 3 foot. Seth, why don't you do the math for me? What is 3 foot times 3 foot times 3 foot? Go ahead, buddy. I checked it for you.
I believe it's 27 cubic foot.
27 cubic feet in a cubic yard. So when we design for a concrete mix, we have to design within that 27 cubic foot block, that known volume. Hence the reason this is called the absolute volume method. Are you raising your hand or just sticking your thumb?
No, go ahead.
Okay, sorry. So we call this the absolute volume method because we have to take certain portions of that 27 cubic foot block. Certain portion goes to air, certain portion goes to sand, rock, cement, water, and admixtures. But we can't design for more than that 27. When we sell our concrete, we actually use that as a way to measure or verify that the concrete that was ordered is the concrete that was made, is the concrete that was transported, is the concrete that was delivered down the chute into the formwork. And what is that called, Seth? Yield. Good job, Seth. Which is our total weight of materials on the batch ticket divided by the unit weight of our concrete measured on the job site. So, for instance, if our total weight of our concrete is 3,930 pounds, which we'll figure out here in a little bit, and we divide that by our unit weight, let's say somebody measured the unit weight and it's 142 pounds per cubic foot. We do 3,930 pounds per cubic yard divided by 142 pounds per cubic feet. And what we end up getting, the pounds cancel out. The cubic feet goes to the numerator, the cubic yards goes to the denominator, and we're left with 20, or some number here in our case is 27.7 cubic feet worth of material per cubic yard of concrete. Now, what that means is we gave them a little bit too much. We didn't shortchange them, which is much better because, hey, there are contractors that will see a 26.8 and be like, whoa, I just bought 2 million yards and you shorted me 0.2 cubic feet. It adds up. I just want my money back. So that's where that comes into practice on the flip side of it. But again, going back full circle, what we're designing is 1 cubic yard, 27 cubic feet. Now, the problem is, if you've never done it before, where the heck do you start? Okay. The concept generally, hey, John, that's cool. I get it. And I'm going to imagine that everybody in this conversation understands that concrete generically is made up of 5 materials, right? Cement, water, rock, sand, and come on, Seth. Cement, rock,
Cement,
sand, water. What's the last one?
You already said rock, sand,
cement,
air.
Rock, sand, air. No matter what, we don't have to design concrete with admixtures. We don't have to use a single effing admixture, but there will always be air in concrete. So my assumption is that this group at least knows that, and I don't have to go into what the raw materials are besides what we're going to do in the design. Is that fair?
Yes.
Cool. Any questions before we move forward with the design?
No, I will ask questions as you go.
Oh, here we go.
All right.
So there are 4 design methods you can use. Portland Cement Association, the American Cement Association has one. Darwin and Mendez have one in their textbook. The American Society of Civil Engineers has one. And then my favorite is ACI 211.21, and it's recently been updated, I think, in the last few years. Hold on a second. I love it. I call it Choose Your Own Adventure. And, I'm very vocal about the authors behind many of these ACIs. This is one of my favorite ACIs, and I absolutely love the authors. I mean, the authors are just there's some amazing authors in here. Kevin McDonald, Chelik, Larry Sutter, Tyler Lay, Jay Shilestone, Katie Bardajan. You've got people. Did you know there's something called the Shilestone method? These are
not told till today.
Yeah, I mean, well, it's a way to design concrete, specifically for a certain type of concrete, but still a way to design concrete. So there are people who helped, clean this up, which it hadn't been worked on since 1991, but the method behind this is really up to date, especially with admixtures. So really, really love this method. And it's a really good read. Like for our readers at home, what I'm showing Seth now is I pulled my version of the 211 out, and it's beat up because I read this thing all the time. Now, you compare that to 323, I mean, the cover is still shiny because I can't stand reading it. I read it when I have to. This thing, freaking love it. Anyway, okay, so I recommend readers get this. It's a great freaking manuscript. All right. So, do you mind if I get into what we're doing today?
Yeah, you're going to walk us through that, right? The absolute volume method?
Well, specific to a customer. So imagine, if you will, you were just hired. You got fired from your job at Baker, Seth, and now you're working for Mark McCoy's Ready Mix or Jon Belkowitz's concrete precast plant, architectural cast stone. And I say, hey, man, no, Ready Mix plant. I said, I need you to design a mix for me. It's going to be a 6-inch thick interior concrete slab. I've got the worst finishers in the world, so I need you to design the maximum slump allowable within this guide here for ACI 211. My compressive strength is 4,000 PSI. I don't need you to remember this because I've got it all written down here. 4,000 PSI at 28 days, not an air and train mix. I got a 57 aggregate, and that's crushed, right? Crushed aggregate, so it's a bit angular, and I can give you all the aggregate properties. But I need you to design me a bookcrete mix that I can take to my lab, do a couple run-throughs, dial it in, and then we can dial it into the plant. Cool? Where the hell do you start?
Yeah.
So in this presentation, what I do is I'm going through the different tables that take you through the decision-making process through ACI 211, and then we're going to go through some of the math. So what Seth has got is paper, pencil. He's got his TI-30X2S calculator, right, Seth?
Yep. Sounds good.
Doesn't sound like he does. And we're going ahead and we're going to actually do the math together and see if we come up with the same answer. Fair?
All right. I'll try to stay up with you.
Cool. Well, you don't have to try. We're going to do this together. So the great thing about ACI 211, the first thing that it starts out with is the first thing that our customer really made important, which was the slump. And that's table 5.3.1. And it's called typical slump ranges for concrete without water-reducing admixtures.
So
just water alone. Now, the reason why we do that is no two chemical admixtures work the same. Even when it comes to water-reducing, and the water that we're going to talk about now that's associated with slump, and then you'll see some other things, goes directly back to our strength and hence our durability, or in this case, our durability. Questions? So in our table, and Seth, you can't see this right now because he doesn't allow me to share my screen. Not nice guy. It gives you different options, 4 of them to be specific. And those options are based, there's slump ranges, 1 to 4, 2 to 4, 2 to 5, 3 to 5, and they're based on the type of construction. Slip formed is construction 1, then mass concrete, and then we have this huge selections of pavements and slabs, plain footings, caissons, substructure walls, reinforced concrete, foundation walls, and footings. And then we have beams, reinforced walls, building columns. Now, those two, the first selection has a 2 to 5 inch slump range, and then the one below that has a 3 to 5 inch. So, I mean, the maximum on both of them, whatever we wanted to call this, whether it's a slab or some reinforced structure, the maximum allowable here is a 5-inch slump. Cool? So when it asks what our slump is, the answer is 5-inch. We're going to underline it once. Have we done any true mathematics yet?
No, we're just picking slump.
No, we're choosing a portion of our adventure.
All right.
Nice.
You're really nerding out today.
I'm okay with that. It's going to get nerdier. Hold on. The second part of this is where we choose our water and our air content based on 3 things. I apologize. Whether or not we have air, non-air and trained concrete, our maximum size of our aggregate, which in this case, we have non-air and trained mix, they told us. The second thing is our aggregate size, which we know is 1 inch. And the third thing is what? Our slump. So what we've got right now is that value. We have a table here that has a non-air and trained version up top, has an air and trained version on the bottom, has slump on the left, maximum sized aggregate, and through that matrix, you line it up and it tells you how much water per cubic yard. And here we've got 330 pounds per cubic yard for our 5 to 6 inch slump with a 1 inch aggregate. Now, consequently, this table also gives you your entrapped air content. And here we could just call it air content. You go to that bottom of that top section, and for a 1-inch aggregate, our entrapped air content is 1.5%. Again, have we done any math?
No, you just picked off of the table based on what you needed. So based off of the slump you wanted, and if you're doing air or non-air, right? There was a third thing?
Non-air, air, and then your aggregate size.
Aggregate size, max egg size, right?
Now, you might have to do a little homework. They'll tell you it's a 57 or 67, blah, blah, blah. That's homework. That's easy. But outside of that, I mean, again, we haven't done any major math, and we're 1/6 the way through this design.
There you go.
It's awesome stuff. All right, so the next thing. Our next table 5.3.1, is adjustments to estimated water content for various conditions, including rounded aggregate, air content over the entrapped air, water reducer, high range water reducer, blah, 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 blah. Temperature decreases, even if we want to increase the slump by an inch or so, or for every inch we want to increase it. So there really is like a lot of, what do I want to take with me on this adventure type choices that you can make in this table. And that's what I love about this new version of the 211. I mean, now it's taking it from the guesscrete into the closer crete within our book crete. So when we were designing it without consideration of admixtures, we were doing a lot of guesswork on what we have to do with the water content based on our admixtures. This new table, whether it's admixtures, rock content, air content, I need to bump up the slump, there was really no direction. Now this gives you a direction. Does that make sense?
Yeah, following
Gets you closer to the finish line, or gets you more efficiently closer to the finish line. So here, we've got a mid-range water reducer. Now with the mid-range, we're going to subtract our water content by 5%. So it says in the table. Okay, so we write down minus 5%. We have crushed aggregate, so we don't have to worry about rounded aggregate, which is in the table. We're not playing with the slump. We're not playing with the air. We're not playing with the temperature. So the only thing we have to take into account on our estimated water to refine it is subtracting 5%, because we are going to use a water reducer. Cool?
All right.
The next step is based on strength. What does the water cement ratio need to be to yield our 28-day strength? And bear in mind, we're not going to take the stance of, well, we're the ready mix provider, and according to ASTM C94, we need to have a certain standard deviation. We're not playing that game. We're just going to say they ask for 4,000. We'll let the ready mix provider do that, okay? It happens to be that you're the ready mix provider, but we're just going with the standard 4,000 PSI mix for now. Okay, so we needed a 4,000 PSI, and in this image, it gives you a table that goes through 2,000, 3,000, 4,000, 5,000, 6,000, 7,000 PSI increments. And it gives you water cement ratios, whether you're using non-air entrained concrete or air entrained concrete. And for us, we're using air entrained concrete. And you remember what our strength was?
4,000.
So in this case, when we use it tells us we need a water cementitious ratio of 0.57. Okay, so again, we're just writing that down. Now, there's another table that says, hey, if you've got structures that are continuously wet or exposed to sulfates or seawater, or has a concrete cover less than 1 inch, there are certain checks that you've got to have. You can't have a water cementitious ratio lower than either a 0.4, a 0.45, or a 0.5 for certain structures in these freezing and thawing and sea environments. Do we need to worry about those?
For your slab? No.
No, it's an interior slab. Doesn't really matter. Okay, can you hear me right now?
Yeah.
All right, my headset just died. So we're going to stick with our water cementitious ratio of 0.57. And I believe this is the last table we've got to run through. Now, this table is the ugliest one. This table makes you want to stay in bed in the morning or just jump in the jacuzzi. The name of the table is the bulk volume of coarse aggregate per unit volume of concrete. Who the heck? You just need a better title. It's a very confusing title.
Yeah.
And then when you look at the table itself, what you're doing is you're taking the fineness modulus of your sand, comparing it to your maximum sized aggregate, and then from there you're picking this ratio that goes back to how much coarse aggregate do you want in your concrete, right? So the number it gives you, whether it's, what I think the highest number is 70 or 82 and the lowest number is 0.44. So it's either it tells you to put 82% of your concrete is going to be rock, your coarse aggregate, or as low as 44% of your coarse aggregate or of your concrete is your coarse aggregate. Now, what do you think, Seth, changes the amount of coarse aggregate? And by the way, the column is sizes of aggregate. So it starts at 3/8 of an inch and it goes up to 3 inch, right? And then in your rows up top, it goes from sand with less fines in it to sand with more fines in it.
So size of each?
Right. Yes. Damn. See, folks, this is why he's the guy who hosts these freaking podcasts, because his brain works that freaking quickly. You're so smart.
Good teacher. Keep going.
So yeah. So if I have a really coarse sand with no fines in it, and my aggregate is really, really flipping small, I'm gonna use 50% of my concrete is gonna be my coarse aggregate. Now, if I make that sand really, really fine, like just put a whole bunch of fines in it, then 44% of that concrete is going to be my 3/8 inch aggregate. Right? A whole bunch of freaking fines in there.
Yeah.
We want to reduce the amount of fines. That's one thing we know in concrete. Reduce the amount of fines as much as we can, because fines, or get us the balanced amount of fines. That's where you have the Shoutout method, the tarantula curve, the Lisa model, the gradation envelope theory. All of those refine what we're doing here. This is a very basic concept of those different methods. Now, if we have a 3-inch aggregate, so a really coarse or a big aggregate, and we have a very clean sand with almost no fines in it, we need a bunch of our coarse aggregate. 82%, that's the biggest number. Now, if we start making a dirtier sand, we can drop that to 76. Does that make sense?
Yeah.
That combination. So for us,
makes sense.
Our fineness modulus was somewhere around 2.6. Now, the thing is, I say somewhere around. The fineness modulus in these tables goes from 2.4 to 2.6, 2.8, and 3.0. So if you're closer to 2.6, traditionally, just use the 2.6. You could do linear extrapolation to find out the exact value, but going from 2.6 to 2.8, you're going up 2% in your total volume. And you'll find out that's not much. But using our maximum size aggregate, which was 1 inch, and our fineness modulus of our sand, which is 2.6, it gives us a value of 0.69, which means that our concrete mix, 69% of it will be our coarse aggregate. We have not made a single decision, we have not done a single calculation yet, have we?
Not yet.
All right. So I just wanted to go through our numbers. Our slump, we said 5 inches.
Yep.
Yeah. Our water, we figured out, was 330 pounds per cubic yard.
Yep.
Our entrapped air content is 1.5%. Did you get that too, or did you miss that?
I missed that one, so I'm writing it down.
No. Just, did you remember where that was in the table, though?
Yeah, that was near the beginning.
Yeah. Okay, good. I was just making sure of that. So it's 1.5%. Our water adjustment, because we're using a mid-range, we're doing a -5% on the designed water. Cool?
Yep.
Our water cement ratio was 0.57. We didn't have to worry about any checks. And our percent of coarse aggregate was 69%, but we're going to write that as 0.69. Questions before we get into gymnastics with math?
Yeah, the 330 pounds of water does not reflect the reduction of 5% for the mid-range, right?
Oh, that'll be one of our calculations.
Okay.
Are you ready to do gymnastics with mathematics? Or what I like to call mathematics.
Oh boy. Here we go.
Okay. So the first, calculation we're going to do is that water reduction. Okay. So we start out with, we're going to call this our new water. It's going to equal our old water, which is 330 pounds. Are you writing this down and doing the math? 330 pounds per cubic yard?
Uh-huh.
He's not doing the math, folks. If you're listening in your car, 330 pounds per cubic yard times the quantity, 1 minus 0.05. Now, if you don't know what that means, you can, in lieu of writing that, I'm erasing and I'm rewriting. You can write 100% minus 5% all over 100%. Same difference. Now, when we do that, Seth has got his TI30X2S. We're doing 330 times, as it turns out, 0.95.
5.
So our new water is 314 pounds per cubic yard. Seth, did you get that?
Is it 313.5 and you round up?
Yeah.
Okay.
That computer can definitely hold a decimal point for pounds per cubic yard. But let's be realistic. We can't measure that.
Right.
And with a true level of uncertainty, that 0.1 pounds. All right, so that's item number 1. Let's do item number 2, which is determining our cement content. Now, we know that our weight of water over weight of cementitious, here we're just going to use cement, equals 0.57. We can erase our weight of water because we know it and we can fill it in. That's 314 pounds per cubic yard. Now, we want to measure or determine the amount of cement. The problem is cement's in the denominator. So we go back to 7th grade. We multiply both sides by cement, the word cement. On the left-hand side, where we have 314 pounds divided by cubic or per cubic yard divided by cement, the cements cancel out, and that equals 0.57 times cement. Again, we want cement on its own. So next, we divide both sides by 0.57. And what we're left with on the left is 314 pounds per cubic yard divided by 0.57 equals weight of cement.
551.
Oh, come on. Give me a second. Is that what you got? Good job. I'm just double checking them, folks. You can't trust these project managers to do math. What did you say? 551?
551 pounds of cement.
Okay. So our cement equals, or weight of cement equals 551 pounds per cubic yard. Okay. Don't forget the units, pounds per cubic yard. Seth, we've gotten into the majority of the math, or excuse me, a minority of the math. How bad is it?
It's not bad so far.
Okay. Come on. Let's keep going before we get tired. It's kind of like a marathon. So we know the amount of cement, or excuse me, we know the amount of water, we know the amount of cement. Now we're going to figure out the amount of rock. Okay? Weight of rock per cubic yard. Now the way we do this, we're going to call it weight of rock. Take what was our percent that they gave us or that we determined? What was it? 6769?
0.69.
So 69% of our rock or of our concrete is our coarse aggregate. Now that's based on a very specific type of rock, and that's our dry rotted unit density. Now they gave that to us early on. I remember I said that, hey, we have a list of all of our material properties, and our dry rotted unit weight is 98.2 pounds per cubic foot. So we got 69% times 98.2 pounds per cubic foot. We need one more thing, and that's to convert this weight from cubic feet to a cubic yard. And we do that by multiplying the entire thing by 27 cubic feet per cubic yard. Now that should make sense because 69% of that is our rock. So we take 69% times our dry rotted unit weight times our volume of concrete, which gives us what? Drum roll. Go ahead, Seth, I'm listening.
No, I'll let you get this one.
Why? Are you embarrassed to be wrong? Lean into being wrong.
No.
Nothing wrong with being wrong. That's why there's erasers on pencils. Look.
I gotcha. So you're multiplying what now?
That 0.69 times something called our dry rotted unit weight of our aggregate, our coarse aggregate.
That's 98.2.
Yes, sir. And then 27 cubic feet per cubic yard.
Got it.
What's that magic number, sir?
See.
Me have this one. Tell me.
Got your teacher now. Times 98. 1,829.4647. Is that what you got?
Yes. So what are you rounding that up to?
I guess you would round it up to make it easy. 1830.
1830. Seems like we got all of our weights. What weight are we missing?
Did we do sand?
Nope. Didn't do sand. Now, it's funny you should ask that because now we get into the scary math. Now, remember how I said this was called the absolute volume method?
Yeah.
Seth, we haven't determined any volumes yet. Guess what we have to do?
Before you figure out the sand?
We've used up almost all of our materials. What we have to do now is determine how much room is left for the sand. The
Okay.
admixtures don't take up any room. Our cement, there's 550 pounds of it. Water is 314 pounds. There's 1830 on the rock, and we have 1.5% air. Like there's only so much left. Somewhere between 7 and 9 cubic feet that's left over for sand. So we got to figure those other ones out, and then what's left over. Does that make sense?
Yeah.
All right, so we have a new sheet and we call it volume. See, I told you, this is an adventure. An adventure. Let's start out with the first one. It's the easiest one. Let's start out with air. Air, we're going to go from simple to really freaking annoying. Air, they told us was 1.5%. So you take 1.5% and you multiply it by a cubic yard, which is 27 cubic feet per cubic yard. How much air do we have in cubic feet per cubic yard?
Okay. So 0.015 times 27.
You got it, sir.
0.41
You got it. 0.41, what? Chickens? Twinkies?
cubic feet
Per
yard.
cubic yard. Because a yard is a linear measurement. A square
Right.
yard is an area.
You're right. Yep. 0.41 cubic feet per cubic yard. That's how much air we got.
Okay, from there we go to water. Now we have 314 pounds per cubic yard of water. Now we need to convert this to cubic feet per cubic yard. And the way that we do that is we divide 314 pounds per cubic yard of water by the density of water, which is 62.4 pounds per cubic foot. Now what happens is the pounds up top and the pounds on the bottom, they cancel each other out. The cubic feet in the denominator goes to the top, the cubic yards in the numerator go on the bottom, and we're left with 314 divided by 62.4, 5.03 cubic feet per cubic yard of water.
Okay.
Now
And that's just a known number, right, for water?
62 at standard temperature and pressure. The unit weight of water is 62.4 pounds per cubic foot. The pounds per gallon is 8.345 pounds per gallon. And then this is the next step. Now the question is, how do you go from the unit weight of water to the unit weight of cement? Because we need to do the same thing. We have 550 pounds per cubic yard of cement, and we need to go to cubic feet per cubic yard of cement. Now, you ready for the trick?
Yeah.
You take the unit weight of water, 62.4 pounds per cubic foot, and you multiply it by the specific gravity of cement, which the specific gravity of cement is 3.15.
Okay.
When you multiply 62.4 pounds per cubic foot by 3.15, the product is 196.6 pounds per cubic foot. Now that's for cement. We're going to do the same thing for our rock, and eventually we'll use the same concept for our sand. Okay? So 550 divided by 550 pounds per cubic yard divided by 196.6 pounds per cubic foot. My pounds cancel out. My cubic feet goes to the top. My cubic yard goes to the bottom. What did you get?
2.8.
Nate, that's what I got. All right, let's do rock. How many pounds of rock did we have?
1,830.
130 pounds per cubic yard divided by 62.4 pounds per cubic foot times the specific gravity of our rock, which was 2.7. Oh, shit. Wrong decimal place. 1830 divided by 62.4 times 2.7. We got a big old number there. 10.86. Is that what you got?
I'm getting there. What'd you get?
10.86.
I did something wrong. Are you multiplying 62.4 times 2.7 first?
Yeah, that was 168.5.
Okay, that's what I did wrong. 86? Is that what you
got
said?
it.
Yep.
Second to last part. We're almost there, man. You're almost done designing your first concrete mix. So remember what I said about the sand? The sand is what's left over.
Yeah.
So you got to add everything up. Point the air, the water, the cement. What's that?
I sent him back.
Oh, hi, babies. Hey, Jamie. And nobody ever says hi to me. You notice that?
I did. I said hello.
Okay. So
Your kid.
hold on a second. What's up? What do you get?
So we're adding up 0.41 plus 62.4.
No.
No? Or, sorry,
0.41 plus
plus
5.03.
0.03. Yeah.
Right. Plus 2.80 plus 10.86. And that gives us a certain amount of cubic feet per cubic yard.
19.08.
Yep. So from there, it's 27 minus 19.08. That is the amount of volume we have left for our sand. Drum roll, please.
7.92
A good looking.
pounds per cubic feet. Foot.
No. That's cubic feet per cubic yard.
Oh, okay. Cubic feet per cubic yard. All right.
Okay. So then the next question begs, how do we determine sand, the weight of sand from this? And as easy we've already done, our weight of sand is going to equal 7.9 cubic feet per cubic yard times that unit weight of water, 62.4 pounds per cubic foot, times our specific gravity of sand, which in this case is 2.59. Our cubic feet and cubic feet cancel out. 7.29 times 62.4 times 2.59. And I'll do this one. We got 1,178 pounds per cubic yard. I'm going to call it 1,180 pounds per cubic yard
7.92
times.
times 62.4 times 2.59.
Yep, because that's our specific gravity.
I get 1280.
Let me do it again. No, it was 7.29. Is that what you said?
No, I said 92. Is it 29?
Did I do? Wait. I might have done the wrong math. Dyslexia at its finest. Yeah, it's 1280.
It's 92.
Did you get 1280?
1280.
Okay. Look at that. See? That's where they put erasers on pencils. Okay to be wrong. So that's 12. So 1280. So what's our final mix? And this is in pound per cubic yard. We have cement, water, and sand. What do we got, good sir?
So cement is 551
Sure. At 550.
or 5, yeah, whatever. Pounds per cubic yard. Water, we did with the water reducer, we reduced 5% with the mid range. So we came up with 314 pounds.
Mm-hmm.
And then rock came up with 1,830 pounds. And then sand, we just did 1,280 pounds per cubic yard.
Okay. Congratulations.
Wow. We did that under an hour.
Okay. Now here's the thing. What we did is a design mix.
Uh-huh.
We do not have the batch mix. And the batch mix, we change up our rock weight and our sand weight based on the moisture content. And then we change up our water weight based on how much rock and sand or how much water is being brought by the rock and sand. We're not going to do that today. That's episode 2.
Uh-huh. That's level 2.
Level 2. Well, it's the second part of it, but yeah.
Okay.
So far, though, this wasn't that bad, was it?
No, it's not terrible.
And you could even imagine a way to create some type of Excel file or, I mean, quite honestly, calculator and pencil and paper, this is not hard. And then when you start knowing a material, like when you start doing enough mixes, you'll recognize that, okay, interior slab, you're at 550. Exterior slab, because you got air and trait, you're probably going to have to bump it up like to 580 pounds from 550 pounds because you got air in it and you have to compensate for that strength because of the air with a little more cement. And because of that, you got to drop your rock and sand down because you just pulled that yield from somewhere. So once you start learning your materials, you don't need ACI 211.
Right.
And once you really learn the concept behind it, again, you stop needing this. This is for, hey, I've never designed concrete before. I want to learn how, or I've never used these materials and I need a good starting place or somewhere in between.
Cool.
Okay.
Well, I appreciate it.
Yep. Next time. I wrote it down.
Next time we'll do so there's adjustments you got to make for the batch mix. Is basically what we're going to talk about.
And then we'll do the mid-range water reducer calculation.
Okay.
Sweet.
All right. Well, thanks for coming on the show today. I appreciate it.
Sir, thank you for having me.
Yes, sir. And folks, until next time, let's keep it concrete.
Thanks for joining us for another episode of the Concrete Logic Podcast. If you got value from the show, here's how you can provide value back to support the show. Visit concretelogicpodcast.com and click the donate button to send value back. All dollar amounts are truly appreciated. And now, to close out the show, here's Mike Dunton.
Ring, ring, that alarm always sings. Couple hours before the sun comes up. Open up the side, put some diesel in the lights and wait till the trucks roll up. Yeah, this ain't how most folks live their lives. Dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5,